Think about the graph of y equals 1 over x. It's a hyperbola, and it seems to approach 0 as x gets extremely big or small. This makes sense. For example, if x is a big number like 1000, y is very small. Similarly, if x is negative 1000, y is also very small. So we would say as x goes to infinity, y approaches 0. We define this to be a limit, what y approaches as x approaches some value. At a first glance, limits seem to be pretty simple. If we wanted to find the limit of y as x approaches some value, we would just plug in that value. Although this strategy works pretty well, we will see that we need more than just plugging in many problems. But before we take a look at some examples, we should know some limit notation. We define the limit of a function f of x as x approaches some value a as shown here. Feel free to pause the video so you know how this works. Now that we know how to easily write limits, we should note some basic limit properties. For the most part, the limit of a sum is equivalent to the sum of the individual limits. This also holds true for subtraction, multiplication, division, and exponentiation. However, we need to be careful with division, because we do not want to end up dividing by 0. We will deal with those situations later. Let's take a look at a basic problem. Find the limit of x squared plus x over 2x squared plus 5x plus 8 as x approaches infinity. Because of the properties of limits, we can write the expression we want to find the limit of in terms of expressions we already know the limits of. In this case, we can multiply the top and bottom by 1 over x squared. This gives us 1 plus 1 over x all over 2 plus 5 over x plus 8 over x squared. We already know that the limit of 1 over x is 0, so 1 over x, 5 over x, and 8 over x squared all go to 0. Simplifying, we get that the limit is 1/2. This strategy is pretty useful for functions that are the ratio of polynomials. In cases where the polynomial in the numerator has a higher degree than that of the denominator, then the function goes to infinity as x approaches infinity. This means there is no limit. In cases where the polynomial in the numerator has a lower degree than that of the denominator, then the function goes to 0 as x approaches infinity. This should make some sense. Just using some simple logic, we should be able to figure this out. Now, what if we want to find the limit of an expression as x approaches some finite value? There are a number of ways we can do this. The most analytical way is to factor the expression and then simplify. For example, if we wanted to find the limit of x squared plus 5x plus 6 all over x squared plus 3x plus 2 as x approaches negative 2, we would first factor. This gives us x plus 2 times x plus 3 all over x plus 1 times x plus 2. We can cross out x plus 2. We can only do this because we are trying to find the limit as x approaches negative 2, so x plus 2 isn't 0. Now we have x plus 3 over x plus 1, in which we can plug in negative 2 and get that the limit is negative 1. Notice that if we had plugged in x equals negative 2 into the original expression, we would have gotten undefined. Usually a strategy of simplifying like what we did before is useful when the expression in the numerator and the expression in the denominator are both 0 when we plug in the value that x approaches. We will refer to this as a 0 over 0 case, in which we have to do more work to find the answer. There are 3 basic possibilities for a 0 over 0 case. One results in no limit, which is infinity, one results in a limit of 0, and one results in a limit of a non-zero finite value. Each of these corresponds to when the numerator approaches 0 faster, slower, or the same speed as the denominator. One of the more interesting things to take limits of are the trigonometric functions. The limit of sine of x or cosine of x is not that intriguing, as these functions are just waves that oscillate back and forth with no limit. This is known as a divergent function. But an interesting problem is solving for the limit of sine of x over x as x approaches 0, where x is in radians. The first thing we do is plug in x equals 0, and we quickly realize this is another 0 over 0 case. We'll need to do some work to figure out what the limit is. While the solution for this problem that we'll be going over with is certainly not rigorous, it does make sense logically. The first thing we do is draw a unit circle, which is a circle with radius 1. It will help us to figure out what the answer is intuitively. Now draw an angle as shown. The height of this angle is sine of x, and the curve that the angle subtends is x. This is only true because we're using a circle with radius 1. Now imagine what happens as x gets smaller and smaller. The curve that the angle subtends will slowly become more and more like the line that defines sine of x. Essentially, the curve gets flatter and flatter, and so logically the answer would seem to be 1. We can check this by plugging in values close to 1 for x, such as x equals 0.999 or 1.001, which confirms that the limit seems to be 1. We can use the fact that sine of x over x approaches 1 as x approaches 0 to find answers to many other different trigonometric limits by writing the expressions we want to find the limits of in terms of sine of x over x. I might delve deeper into these types of problems in another video. And that's it. Thanks for watching. I'm currently trying to get a better upload schedule, but like I've said in older videos, I'll probably have to post less often, maybe bi-weekly, due to longer editing time. I hope you enjoyed the video.